Thank you. And also from my side, thank you to the organizers for giving me the chance to present my work here. I'm Laura. I'm a third-year PhD student at the Max Planck Institute for Radio Astronomy in Bonn. And yeah, I want to show you how I resolve the comfort zone of Sag-B2N1. And I would like to start to talk about a little of my title page. So what you see here in the background is the central molecular zone of our galactic center region. You saw that already during the conference 1 or 2 times. And you see here emission from coal dust. And as you may know, coal dust traces star formation, and that is why Sagittarius B2, or also Sag-B2 as I will call it throughout the talk, is glowing up here. Sag-B2 is one of the most massive star forming region in our galaxy. And if you zoom in, you find multiple sites of star formation. Amongst them is Sag-B2 North. And if you zoom in a little further, you'll find the main hot core, the main protostar, the main hub, whatever you want to call it, Sag-B2N1, which is the source of interest in my work. And what I'm looking for are complex organic molecules, or COMs, and I want to find out how they arrive in the gas phase and observe their journey in the gas phase and what happens to them. So first of all, I wanted to introduce the complex molecules again. You heard of them during the conference already as well. So complex organic molecules consist of at least 6 atoms. To call them complex, one of them has to be carbon for the organic part of it. And just in case you wondered, how complex can the interstellar medium become? I show you a table of molecules detected in the Milky Way from 2021. The columns for the simpler molecules, they extend much further south. We are interested here in the complex molecules, and you also see they have year tags. And if you compare the molecules, the number of complex molecules that we knew before the year 2021 and the ones that we detected only last year, the number is really amazing how many molecules have been detected only last year. And the rate is increasing due to the new facilities and the upgraded telescopes, which is really great. So it gets more and more complex, the interstellar medium, and it gets more interesting and necessary to understand what we can learn from complex molecules. And I also don't have to tell you why we're interested in studying COMs. We are consisting of them, and we are curious about finding out where we come from and how much of complex molecules is inherited from earlier phases of star formation where we see them for the first time, and so on and so forth. You also heard that many COMs have first been detected in so-called hot cores or hot corinos, which are basically the regions that are bright in COM emission around high mass and low mass protostars. And they're usually associated with a temperature of 100 Kelvin or higher, which has to do with their formation. Because many COMs are thought to be formed on dust grain surfaces, that is, before the onset of the protostellar heating, simpler molecules can freeze out onto the dust grain surfaces, they build up ice mantles, and then at some point the protostar is born, starts heating its environment, and then the simpler molecules on the grain surfaces, they can get mobile, they can find each other, and they can build up more complex species. And they reside there on the complex, on the surface, as we're below 100 Kelvin. And then at one point we hit the 100 Kelvin. And that is when water desorbs. Water is the main constituent of the ice. And as it desorbs, that is, it goes from the grain surface into the gas phase, it uncovers the complex species, and they can more or less co-desorb, so simultaneously desorb with water into the gas phase where we can observe them. That's a great theory, that makes sense. I think it also has been shown in the lab, but we lack the observational evidence for that, mainly due to the limitations of angular resolution of observations. And also this theory has faced some challenges. On the one hand, we see more and more detections of COMs in cold gas, that is in dark clouds like TMZ1, or also in quiescent clouds, quiescent in star formation like G0693 in the galactic center region close to Sag-B2 North, actually. And on the other hand, that points, that triggers the thought of non-thermal desorption. And on the other hand, we see in chemical models that there is thermal desorption, but it may happen in a different way. And for that, I show here a model of one of my collaborators, Rob Garrett from the US. And what you see here is the abundance of molecules. So the column density of the molecule divided by the column density of H2 as a function of time. So as the star evolves and gets more powerful, also the temperature rises. And what you see is the abundance on the dust grain surfaces in dotted lines, and the abundance in the gas phase in solid lines. And you see there is a steep increase in the gas phase abundance when the desorption happens. And so this transition from dotted to solid line basically shows you the position of the desorption. And you see that this transition happens at different temperatures with different comps. And what the authors concluded is that the desorption process happens depending on binding energies of the comps. So the comps can diffuse to the surface of the grain, and then at different temperatures that corresponds to their binding energy, they can desorb into the gas phase, so at different temperatures. Also, that hasn't been proven observationally due to the same reasons. So you see there are a bunch of theories, but we don't know for sure how they really get into the gas phase. And that's where my work comes in. So what I want to find out is, does desorption happen due to the temperature increase of the protostar, depending on binding energies, or co-desorption with water? Do we see any signs of non-thermal desorption due to shock chemistry induced by increasing shocks, by outflows, by overall turbulence, or whatever it may be? I want to look at various comps to see if there are differences between them, and if so, why that is, of course. And well, SAGP2 N1 is a great source to study that. So we see it here in dust continuum. It's basically the red blob corresponds to the hot core. It shows we know it is a hot core. It shows the comma emission. It has an outflow in that direction. It has filaments that you can see here in cyan dashed lines, through which probably accretion happens onto this main hot core. So it fulfills all the requirements to study all the possible desorption processes. We use the ReMoCA survey for that. Stands for Re-Exploring Molecular Complexity with ALMA. We observed the complete 3 millimeter window, and we have angular resolution of 0.4 arcseconds or less. And just to show you how the spectra look like, this is 2 gigahertz out of 30, and all of the spectra look like this, full of lines, like a line forest. There are many emission lines of comms, and it's a lot of information hidden in these spectra. And I show you some of the results right now. So first of all, we look at the comma emission, so the morphology of it. So that's, again, the hot core N1. Here's the list of molecules that I studied throughout this work. And you see in the top row, typical oxygen-bearing comms: methanol, ethanol, dimethyl ether, methylformate. And you see they're all very extended and very structured in emission. It actually follows kind of the morphology of the dust continuum. On the other hand, we have nitrogen-bearing comms like ethyl cyanide and vinyl cyanide. They are more compact, less structured. And on the other hand, then we have molecules that show morphology somewhere in between. They are more compact, but they also show some kind of structure, like, for example, acetaldehyde here, or also methyl isocyanate and also formamide, which I don't show here. So you see, first result, we actually see differences in the morphology, roughly between oxygen and nitrogen-bearing comms. And in the following, we want to find out why that is and how we can get the desorption process into the game. I can't show you much of the analysis that I've done on the methodology. I just want to tell you, I really wanted to focus in this project on the thermal desorption process, and I wanted to find out if it happens depending on binding energies or alongside water at one temperature. And to do that, I chose some positions to the south and to the west of the continuum peak position here. And I created, on the one hand, population diagrams, and I also modeled the spectra under local thermodynamic equilibrium conditions. And from both these methods, I get the temperature and the column density at each position for each com. And I can basically then see how the temperature and the column density behaves as we go further away from the protostar. I can't show you this here for time reasons. We go right away into the abundance profile. So the abundance here as a function of temperature, where the temperature comes from these profiles here. And that is how it looks like. There's a lot of information in here, both directions, all the comms. What I created is a kind of a summary plot here that you can also find in my paper that I submitted only a few days ago, so that takes some time to get published as well. I just wanted to draw your attention to basically 3 regions that we identified. There is the region at really high temperatures that we call the gas phase evolution, and we see many differences between, not that many, but some differences between the comms. For example, we have for the oxygen-bearing comms like methanol, the yellow one here, we see decreasing abundance with increasing temperature. For example, for acetaldehyde, the red one here, we see increasing abundances with increasing temperature. Also for vinyl cyanide, the black one here. And then, yeah, some molecules are somewhere in between. And then we have a region at 100 Kelvin where we have this turnover point where the abundance really more steeply increases for many molecules, also here methanol. And then at low temperatures, we have something that, spatially speaking, before the steep increase, we have here some plateau-ish values that are non-zero at low temperatures. And so we now go through some of these regimes in more detail. So what you see here again from the introduction, as you remember, is the model from Garrett et al. 2017. And yeah, the steep increase I said in the beginning, corresponds to the desorption process. What you see here now in direct comparison is that it does not happen at different temperatures for different molecules, which corresponds to this region here. It happens at roughly 100 Kelvin for many molecules. So that is inconsistent with the binding energy dependent thermal desorption. And I thought, well, okay, it doesn't match the models, but anyway, but I knew that Garrett was working on new models. And at some point he reached out to us and sent us the manuscripts, his new manuscript that is now published. And that is what I saw in his new models, which is just great because his new models predict that we see actually co-desorption with water at one temperature for all the molecules. Which is due to the fact that he turned off the diffusion of comms, so they cannot diffuse from the inside the ice mantle to the surface, and where they could potentially desorb according to different temperatures, according to their binding energy. So he turned that off. The molecules are trapped under the ice, and they can only desorb when water desorbs. And so we conclude here that we actually see thermal desorption at one temperature, roughly 100 Kelvin, which is very likely alongside water. If we move on to the gas phase evolution here, I show here also another plot from his paper, from Garrett's paper, where you see the rate of formation, destruction, arbitrary units along like the evolution of the protostar. So before the protostar is born, warms up its environment. We have the H2, desorption of H2 and the comms. And then we have this at high temperature, the gas phase evolution. And yeah, here, for example, you see the oxygen bearing comms. For example, methanol and ethanol, you see mainly they are produced before the onset of the protostellar heating in the cold phase under the ice on the dust grain surfaces. Then nothing much happens. In the warm-up phase, they desorb with water, and then in the gas phase, they are destructed, they are destroyed. And that's exactly what we see in our observations, that we saw abundances that drop with higher temperatures, which is very well in agreement with the models. On the other hand, for example, we have, thank you, vanillin cyanide here. Some fraction is produced in the cold phase, but the main fraction of the molecule is produced at hot temperatures in the gas phase, which explains the continuously increasing abundance profile for this molecule. So also that fits perfectly, which is really great. What about the other comps? I show here an example from methyl isocyanide, which does not 100% fit with our observations. So in the model, it is only produced on dust grain surfaces during the warm-up, as you can see. It co-desorbs with water, and then it is destroyed in the gas phase. In the observations, we rather see an increasing trend of the abundance with increasing temperatures, which points more to maybe gas phase formation. There is no gas phase reaction included into the model, but there's a candidate from that we saw in other references that may work, that may be efficient at high temperatures. And if included to the model, we may see an improvement between model and observations. And then just briefly to the low temperature part. So we have two theories that what may happen here. On the one hand, we may see non-thermal desorption. We have an outflow, we have accretion, which could induce shocks. But we are not quite sure if that really happens here at that point, at that distance from the protostar and that position in the hot core, because we don't see any evidence in the morphology nor the temperature whatsoever. What we have, however, is enhanced cosmic ray flux, as we are in the galactic center region, and it was also shown that we have enhanced cosmic ray flux in Sagittarius B2 North. So that may either produce comms, but it can also destroy comms on either side. And we may also have enhanced turbulence, large-scale turbulence, due to the galactic center location of Sagittarius B2. On the other hand, we may see, so instead of the non-thermal desorption, we may see another thermal desorption process that happens here another plot from Rob Garrett, and we see here the layers of the ice of the dust grain. You see here the outermost layer, so when right before the onset of the protostellar heating, so when it's the coldest, we see that CO freezes out, and then we have CO-rich ice layers in the end. And actually, the binding energies of COMS that are in these layers is reduced. And so as CO desorbs thermally, because it has a really low binding energy, it can desorb at 20 to 30 K. So if there are COMS present in the ice, they can probably also co-desorb with CO at that point. And so we have some abundance of these COMS at these low temperatures. And yeah, so I will not go in detail through my conclusions again, just there's some more information here. You can read it, and if you have questions to that, I'm happy to answer them. The final conclusion from that is we were able for the first time to really spatially resolve the desorption process of COMS and see how they behave in the gas phase, then later at higher temperatures. And I want to say that given the simplicity of the model by Rob Garrett, like not in terms of effort, but in terms of kinematics and 3D structure, it does not take into account any 3D structure. It's a 1D model. It's really great how the model and the observations match. And we also see where we have explanations if something's not working, and some new ideas that could be included into the model. And yeah, I finish here. Thank you very much for listening.
Thank you. That's very exciting work and very close to my heart because I'm doing science also in that region. So it's really cool to see. Are there questions in the chat so far before?
Yes, there are some questions. The first question is, are molecules so large as the COMS expected to do significant diffusion in the ices?
Well, they were, and that was included into the model. I don't know how it works with porosity also. But yeah, I think that was the main idea of Rob Garrett, that he thought, yeah, maybe they're not even able to diffuse, and we turn it off and see what happens. But yeah, I think, but in the model it worked in the previous models, and that's why we saw the results. And but yeah, apparently it might not happen.
Yeah, and then there are a couple of people asking about what is the difference between the two versions of the model, the 2017 one and 2022 one.
There are
new reactions added or new things improved.
There are multiple new implementations. For example, new reactions in either phase, in the bulk ice and surfaces, and also the gas phase reactions. Then the diffusion thing that I mentioned, because that's the reason why we have co-desorption with water now. So there's no diffusion whatsoever, except for H and H2, so the simplest species. And then also, I think adjusted binding energies for some species. So there are a lot. I can refer to the paper. It's really long though, but it's really interesting, but there are a bunch of new implementations that he made there.
And Alvaro is asking a follow-up question. Is this then the final definitive chemical code with all the reliable reactions?
No, I think it's not. No, not final reactions, as I said. Especially for that molecule that I showed here, methyl isocyanate. Oh, is it? It's really sparse right now in the chemical model. And there are also other molecules that do not fit perfectly with our observations. I just show you the beautiful example and just one example that doesn't fit as well. And also for some molecules, we don't have a finite idea yet what's happening, why there are differences between the model and the observations.
Okay, I think there's no more questions in the chat, so I'll take maybe one more. Oh, no, there is one.
There is one,
sorry.
Yeah.
Yep.
Are you taking into account gas phase routes for the ICOMS formation, or only grain surface ones?
No, there's a chemical model for all three phases: the bulk ice, the grain surface, and also the gas phase, and they all interact through various reactions.
Okay, then I ask mine because you were very short in answering things. I was just curious from the observational side. Do you think observations in higher bands to go together with what you saw now in band 3 would make sense to also explore higher temperature ranges, or do you think your band 3 data gives you all information you need?
there's probably a lot more to learn about it. I mean, we also couldn't go to see the on the continuum peak because we dealt with optical depth of the continuum. We couldn't see that. So 100 Kelvin is the highest that we went, or that we saw in the models and our observations. Sorry. So yeah, I don't know if what we can find out still, but it would be great to see at higher temperature what happens with. We also see some differences in the temperatures between the oxygen and nitrogen bearing combs, which we don't know yet why that is. And I don't know how we could find that out yet. The model doesn't help yet. So
great. Okay, thank you very much. Very interesting stuff.